Our lecture today is going to be on experimental errors. How do you detect and, where possible, minimize experimental errors, and how do you quantify them? Now, some errors can be very expensive, and that's why analytical chemists, are trained to be very careful when conducting chemical analysis, so that their data is extremely reliable. Now, in history, you've had cases where analytical chemists or organizations they work for have suffered liability and lawsuits because of experimental errors. And so, in this lecture, we're going to talk about what are experimental errors and what can be avoided and how can they be quantified. So take note of this, while some errors can be avoidable, others cannot be avoided and they can only be quantified. So in this lecture, we're going to talk about which are they that can be avoided and what cannot be avoided. So the objective, for the lecture then is for you to be able to learn the different types of errors, be able to quantify, how to quantify the errors as well in terms of what I'm calling uncertainty. How do you quantify, the error? And also how do you propagate, uncertainties? Because as you guys well know, in most cases, analytical chemistry involves multiple sets of sample preparation, and in each step, there could be an error that results into a propagated error for the final answer. So how do you propagate uncertainties, or how do you propagate errors? And I'm going to show you how to do that. Now, as I've said, experimental error is part of measurement. In most cases, it's very difficult to avoid it, and it can only be really quantified in some cases. Now, take an example of what you already know, the pipette, say, calibration, that you guys already did earlier in the week. Now, you take some data that looks like this, you did trial 1 and you got a value, maybe a volume of 9.9862. And then you tried again, you didn't get the exact same volume, you got a slightly different volume. If you tried it at that time, again, you're gonna get a different volume. And when you average, you do the standard deviation of all those values, and you get, the uncertainty. And so you can see that experimental error is really part of measurement. You just need really to be able to quantify it. Yeah, so in this case, remember, that you should always take note of the significant figures. Take an example of this problem where you average, these volumes and you get that. You do the absolute standard deviation that I hope all of us know how to do using that formula. You get that number. Now, the answer that you report in the end, you have to really account for the correct significant figures. And I can't overemphasize, the importance of this. Some of these numbers are not significant. And so the way we do it is, the first uncertain number, become your last significant figure in your average. So in this case then, I'm gonna round off this, to 0.01. And so my correct mean should be 9.99 plus minus 0.01, because my first uncertain number, which is here, should be my last significant figure. So very, very important. Take note of how you correctly report your data in terms of significant figures. Very, very important. Maybe just to emphasize some more, errors matter. You had this very significant case of a botched testing involving the Zika epidemic. And all of us, know possibly about the microcephaly, a terrible disease, that or condition that results from pregnant mothers that have been exposed to the mosquito-borne virus or the Zika virus. And the CDC recommends that pregnant women that travel or live in areas that are prone to mosquitoes, that carry the Zika virus should be tested, for that virus, so that the babies or the fetus is not affected by this condition called the microcephaly, where the babies are born with extremely small heads, resulting into problems, with brain development. Unfortunately, in the US, in Washington, D.C., there was a botched testing where the reagent that was used, to test this virus was not quantified properly in terms of its concentration. And so up to 400, Zika tests, came back negative. And yet after retesting, some of those negative tests, are actually positive. And of course a lawsuit, was launched, because of that botched problem where analytical chemists, or technicians, are involved. So you see how big of an issue, the importance of the things we do in the lab, such as very clearly knowing the concentration of your standard solutions, what an impact, it can be. And why it's very important also to have the so-called standard operating procedures where every step in your chemical analysis, has been verified and it's followed, very, very clearly. Because the impact, can be very, very significant. And remember, I think in a few lectures ago, I talked about the good laboratory practices and emphasized, the idea, of standard operating procedures that almost every chemical analytical lab really has to follow, so that the data that they produce out there, can be verified. So very, very important. Now, over the years, because of the GLP, the good laboratory practices, actually we've seen largely a decline, in the number of clinical tests, that come out wrong, in the number of botched tests, tests. And that's largely, because of the GLP. For example, in the States, every year you've got up to 13 billion, clinical tests. And using this logarithmic scale, you can see that over time, we have reduced, the number of errors in the lab tests, because of the standard operating procedures, that these labs have to abide by. And we expect, of course, in the future, as an analytical chemist, we are training you so that in the future, the number of errors, can actually reduce. So improving reliability of data, depends on the scientist's ability to recognize and prevent errors, and that's the purpose of this lecture, and also to make intelligent decisions in cases where chemical analytical methods have got certain levels of uncertainty. So again, I emphasize, the significant figures. Anytime you report numbers, take note of the significant figures. I think all of us know the definition of a significant figure. The minimum number of digits that are needed to write a given value in scientific notation, and take note of this, without losing precision. Remember, zeros, before a number are generally not significant. But any zero after any other number, is actually significant, so take note of that. Although I expect you guys know this. And I should say that there will be loss of marks up to 1% for every answer that is given by you without the right significant figure. It's very, very important. Remember, sig figs matter. If at all you're doing an operation, say an addition or a subtraction, now remember, you round the answer according to the number with the fewest, decimal places. A case like this, for example, and of course, when you're doing addition and subtraction, the scientific, notation or the exponent, should always be the same. So after you do the addition, the number should have, the answer should have the fewest, decimal places, of any of the numbers that is involved in the addition or subtraction. So in this case, it should be 2 decimal places because this has got only 2 decimal places. If at all, again, you're doing addition and subtraction, remember you can have the answer with more significant figures. For example, in this case, when you add these numbers, the answer has got 5, 6 figures, whereas the numbers you added, have got only 4 significant figures. And in this case for subtraction as well. If at all you're doing a multiplication and a division operation, now remember the answer is limited to the number of digits in the number with the fewest significant figures. So you do this multiplication, for example, this number has got only 2 significant figures, this number has got 5 significant figures. The answer is limited to the number that has got the lowest number of significant figures, which is these two significant figures in this case. If at all you're doing logarithms, and anti-logs, remember the number of digits in the mantissa, sort of the decimal places here, of the log of x should be equals to the number of sig figs, of x. So again, remember that rule of significant figures when we are doing logarithms and anti-logs. So experimental error, every measurement has some error in it. It has some uncertainty. And so experimental error, quantitatively, it's the difference between the true value, and we have to talk about a little later, how do you know the true value? When you already have said that every number, sort of every measurement has got some uncertainty. So the difference between the true value and the measured value is what you refer to as experimental error. In chemical analysis, the goal is to measure a sample reliably, accurately, and precisely. What's precision? Precision is how well the data distributes around the mean. It's how replicatable your data really is. Accuracy, on the other hand, is how close your data is to the true value. Meaning, the data can actually be very, very precise, but be inaccurate. Meaning the data can be distributed, around the mean, but it's very, very far, from the true value. Okay. But in chemical analysis, we want both reliable, accurate, and precise data. So the way you typically know the data is very, very accurate, again, like I said, is to compare it to the true value. How do you know the true value? The true value is typically known by the use of what you call the standard reference materials that often come from national standard labs. When I give you an unknown in the lab, I know the true value. And the reason I do is because I've analyzed that sample so many times and lots of using different instruments, to confirm there is no bias to the number that I've given you. So it's very, very close, to what they call the standard reference material. And the standard reference material, typically that's how they do it in national labs. They run it many times using different sets of instruments and using different type of chemists, so that you don't have any error, any significant error. So types of error out there. There are three types of experimental errors. You've got what you call systematic error. Sometimes they call it determinate error. There's what you call random errors or indeterminate errors. And of course, there are blunders too, or what they call the gross errors that hopefully, they won't exist, for you. So what's a systematic error or determinate error? These are errors that arise from a flaw in the equipment or from your design of your experiment. Now these errors, very important, they are reproducible, and that's why they are calling them systematic. And so if at all, they are positive, far from their true value, they are always very, very reproducible. And so these errors can easily be discovered, and they can be corrected as well, in most cases. So how do you detect them? How do you discover them? The way you discover them is you run a known sample, where you actually know the actual value. And if that actual value, you get data that is different from that actual value, you'll be able to know that there is a flaw, with the chemical analysis, either with the equipment or with the experimental design. Another thing that you can do is you can run a blank. And a blank, typically is, a sample, that doesn't have the analyte, okay? So it should not have any analyte at all. Meaning, ideally, you should be getting, a 0, for the analyte. And if you end up getting a value other than a 0, then that possibly I have, systematic error. So again, the blank, is a species or a sample that has got all the components in the sample but doesn't have the analyte in it. So analyze the blank. If you observe non-zero results, then you've got a systematic error. Another way you can use to detect, systematic errors is to actually use a different equipment. And if the equipment gives you a different value from what you had previously, then you've got a problem. Another way you can use to detect the error is to give the sample, to another set of chemist or an analytical chemist to do the analysis for you. And sometimes they call that, the round robin experiment, where you take your sample and then you give them to a different set of lab somewhere else, to verify your data. So you can always detect it as systematic error, but how can you correct it? You correct systematic error by calibration. And that is why in the last lab session, that's all what you're doing, calibrating your glassware, and calibrating your instruments, which we're gonna do as well. You can also correct it, by doing other sets of calibration, instruments calibration called standardization or internal standard calibration methods, which we're gonna cover later on, maybe sometimes next week. But the key thing is you correct systematic error by calibration. Now, random errors, on the other hand, are random. They arise from uncontrolled variables, okay? So these ones are distributed such that you've got, sometimes they are negative, sometimes they are positive, okay? So they are always present and they cannot be eliminated. So they are always present. However, you can quantify them. You can know the extent of the random error, and that's a key. You can know the extent of the random error, but it cannot be corrected. However, they can be minimized if you use a better technique. Maybe I'd like you guys to start thinking, what are the better techniques you can use to try and minimize these random errors that are always present in any analytical method. So examples of random errors are electrical noise in an instrument. For example, when you guys were using the analytical balance, sometimes it will keep fluctuating. A big problem, it's always there. It could be minimized, but it cannot be completely eliminated. Think about it, when you're doing your pipette aliquot, there could be subjective reading of the scale, for that graduation line. So again, that is an error that would vary, between individuals depending on how they are reading the scale. So again, that's a random error. Gross errors, of course, these are accidents, that hopefully can be completely eliminated. And there's a whole list of them, instruments are breaking down, calculation errors, that's very common, and so forth. So if you look at, most of the errors out there that result in botched tests, you're gonna find in most cases the challenge is in the calculation errors. That's the biggest error out there. And then the procedural errors. And then maybe the other one is poor precision, and so on. And then things like, poor dilution. And take note of this: significant figures, not adhering to the correct significant figures. So again, you can see all these things that sounds very trivial, like significant figures, play a very significant role in making sure that your data is reliable, which is the crux or the purpose, of analytical measurements. And that's what, analytical chemists are paid to do, to deliver reliable data. So I'd like us to talk now about how do you quantify, especially indeterminate errors. How do you quantify them? And that's what I'm calling uncertainty. Quantifying indeterminate experimental errors. Okay. Now, there are two ways of doing this quantitatively. There's what you call the absolute uncertainty and what you call the relative uncertainty. Now, the absolute uncertainty has got the same units as your measurement. So you take your mean, like what we did before, with the pipette calibration, and then I take my absolute standard deviation, and the number that I get is what I'm calling the absolute uncertainty. It has the same units as, my measurement. On the other hand, you've got the relative uncertainty, which is simply taking a ratio of the absolute uncertainty, and then you divide it, by the mean, by the measured value. So in this case, it would be 0.01 divided by 9.99. Okay. Take an example of these, an example given here, where you've been told, that the mass that was weighed by an analytical balance is 0.1645, and the standard deviation, maybe the analyst analyzed it, say 3, 4, 5 times, and then, he got this mean, and then after they did the absolute standard deviation, they got this number. So to do the relative uncertainty, you just do the ratio. The absolute uncertainty divided by the mean. And that is what you get as a relative uncertainty. Take note of this. The grams have cancelled out. And so my relative uncertainty has no units. It's unitless. In some cases, people would multiply it by 100. And they would call this then percent relative uncertainty, which is 0.3%. So if you look in the literature and you see people calling percent RSD, they refer to this, percent relative standard deviation. Now, as you well know, and as I mentioned earlier on, analytical tests, take multiple steps. And you can have an error in the first step, an error in the second step, an error in the third step, all of which are gonna contribute, to the error, for the final answer. Remember, you do not just simply add up, the errors at all those steps, and sum them up into the final answer. Because as you well know, the random errors, they are random. Sometimes they are positive, sometimes they are negative, and so sometimes they would cancel each other. And so you just don't add them up. Instead, you follow some set of principles, related to the propagation of the uncertainty. And that's what I'm going to show you, the set of principles that you use to propagate the errors if at all you are doing multiple steps in chemical analysis that contribute to the error in the end. So how do you do this? Typically, you use this propagation of uncertainty equation. Okay, this one refers to the errors, and then you square it and you sum them up and you take the square root, of what was summed. Okay, now if the operation, between maybe step 1 and 2 is involving addition or subtraction, this E should be absolute uncertainty. So you should use the absolute uncertainty if the operation is an addition or subtraction. If at all the operation is a multiplication or division, this E that you put, in the error propagation equation, should be relative or percent relative standard deviation. Okay. I'll give you an example, in the next slide.